Welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 4 from the October-November 2023 Cambridge 9709 mechanics paper, which is a paper 4, variant 3. Question number 4 here, we are told about a car which has a mass of 1,600 kilograms, 1,600 kilograms. The car is moving along a straight horizontal road at a constant speed of 24 meters per second and is subject to a constant resistance of magnitude 480 newtons. Find in kilowatts the rate at which the engine of the car is working. Now, the rate of engine of the work done, or the rate at which the work is done, is the power. Okay, the power. So it's going to be basically the power is given by the force that's acting times the velocity. Power is equal to force times the velocity. That's one equation for power. Another equation for power is the work done over time. All right. In this case, we're going to find, the force times the velocity. That tells us the power. Okay. Now, the power is quite a straightforward question because we've got the force, which is 480, and we've got the velocity, which is 24. Okay, so it's basically just 480 times 24, and that will give us our answer. Okay, so we have 480 times 24, which gives us 11,520 watts. Now they want the answer in kilowatts, which gives us, if we divide by 1,000, 11.52 kilowatts. Now, a lot of students are liable to lose marks if you write the answer as 11.5, because this is an exact answer. We don't round it to 3SF, we leave it as it is. We're just writing it in kilowatts, so we divide by 1,000. So 11.52 is our answer. Okay, that's how we should leave our answer. Don't write it as 11.5, don't round it to 3SF. So there's the answer to part A. Okay, pretty straightforward. Now, the car now moves down a hill inclined at an angle of theta to the horizontal, where the sine of theta is 0.09. The engine of the car is working at a constant rate of 12 kilowatts. The speed of the car is 24 meters per second. At the top of the hill, 10 seconds later, the car has traveled 280 meters down the hill and has a speed of 32 meters per second. Given that the resistance is not constant, use an energy method to find the total work done against the resistance during the 10 seconds. So in this question, because they told us that the resistance is not constant, that means the resultant force acting on the car will not be a constant force. So therefore, we cannot use the Suvat equations. All right. So in fact, even if we could use the Suvat equations, the question tells us expressly not to, because it told us use an energy method. So let's just make a little diagram to illustrate what's happening. You have this plane, okay, which I've kind of drawn at an exaggerated kind of angle just to help us understand. You have the angle at which it is inclined, which is theta, and we know that the sine of theta is 0.09, and you've got this car moving down. So it starts from here. Okay, let's call this the point A, and by the point B, it has gone down by 280 meters. Okay, so it's gone down 280 meters. Okay, 280 meters along the road. Okay, this is when time is 0. This is when time is 10 seconds. We know that at A, its speed is 24 meters per second, and at B, its speed is 32 meters per second. All right, and you've got basically a resistance to its motion. Okay, and here you've got the driving force. We can say the power here is 12 kilowatts. That's the power. Okay, now we want to find an energy method. So we're going to use the work energy principle. Okay, we're going to apply the work energy principle, which is basically that the work at the start and the work at the end, okay, are going to be the total energy at the start is equal to the total energy at the end. Now, if there are external forces acting, we have to also include those. So we can say the kinetic energy at A plus the potential energy at A plus the work going into the system, which is basically the work done, okay, which is causing this power at a constant rate, is equal to the kinetic energy at B, the point where we're ending this thing, plus the potential energy at B, plus we can say the work out, which is things like the resistance. So that's what we have to find here. We have to find the work done against the resistance. That is, the work done against the resistance. That's what we're trying to find. So this is what we're looking for. We've got to find what these things are. Now we know that kinetic energy of a particle is a half times m times v squared. We know the potential energy of the particle is equal to mgh. So one of the things we need to do here is we need to find what this height is, the vertical height. The h there is the vertical height. So we need to find what that vertical height is over here between the points A and B. Between the points A and B. Okay, so I need to adjust that so it starts at A there. Okay, so I need to find, basically, that's a right angle. I need to find what the h is. I know that this angle is theta, same as that angle. So I can say that the sine of theta is equal to h over 280. So h is equal to 280 times sine of theta, which is 280 times 0.09. So if you find what that is, 280 times 0.09, that gives us h, which is 25.2. So h is 25.2 meters. 25.2. So now the kinetic energy at A is a half times the mass, which is 1600, times the square of the speed, 24 squared, plus the potential energy at A is given by mgh. So m is 1600, g is 10, and h is 25.2. 25.2 plus the work in. Now, what is the work in? So we know that the power is equal to the work done over the time it's applied. So here we can say the work in is going to be equal to the power times the time. Okay, so the work done is going to be the power, which is 12 kilowatts, times the time, which is 10 seconds. So it's going to be 120,000, okay, joules. So that's plus 120,000. So that's the total energy at the start, including the work that went in, which is from the driving force. And now we've got to find the situation at the end, at B. Now the kinetic energy at B is a half times 1600 times 32 squared. Now the potential energy at the end, because we're taking this as our zero potential energy, is going to be 0. And plus the work, okay, which is going out of the system, and this is what we're looking for. Okay, so this is what we're looking for. So if we now take all of this and we subtract that, so we can say that, let's just work out what this is. It's 800 times 24 squared. So we have 800 times 24 squared, which gives us 460,800. So that's 460,800 plus, and here we're going to have 1600 times 10 times 25.2, which is going to give us 403,200 plus 120,000 is equal to, and we're going to have here 800 times 32 squared, 800 times 32 squared, which gives us 819,200, and that's plus the work out. So we can say the work out is going to be all of these added together minus that. So you're going to have this plus 403,200. Second, let me just do it probably 460,800 plus 403,200 plus 120,000. Okay, minus, we'll take away this 819,200. 819,200, and that should be our answer, which is 164,800, 164,800 joules. So that is the work done against the resistance. Okay, so this is an energy method which we use, and this is very, very important. This is called the work energy principle. This will help us a lot in these type of questions. Okay, so the work in part is anything that goes into moving the object, okay, that goes into adding energy into the system. And the work out is anything which involves taking energy out of the system, like frictional forces, resistance forces, air resistance, and so on. Okay, so here the work in is the power, okay, is caused by the power. So the power is at 12,000, but it's acting for 10 minutes, so it's going to be 12,000 times 200. Why? Because the work done is power times time. Okay, as we know, power is work done over time, the rate of work that work is done at. So therefore, work done is power times time. And the work out is what we're trying to find, which is the work done against the resistance to motion. Okay, so we're not finding the resistance, we're finding the work done against the resistance. If the question said find the resistance, then we would have to take this distance over which it was acting, which is 200, and divide that by 280. So to take the work done and divide it by 280, that would give us the actual force of resistance. But in this case, I want the work done against friction, against resistance. So that's the answer to this question. So I hope that was clear. Other questions from this particular paper can be found in the playlist that will appear in this section over here, the end of the video. Other questions dealing with work, energy, and power can be found in the playlist that will appear in this region over here. You can subscribe to my channel by clicking on this link, and the link over here will take you to a video which explains how to use my channel to find what you're looking for. Thank you for watching, and see you soon.